Do you know what is verification IP in VLSI? Do you know why a robust verification plan is necessary in VLSI with respect to the VIP context? Do you know how general verification test bench is weaker than a verification IP for the same protocol? Want to know about the verification IP using an open example? Our viewer has also requested for this FAQ on VIP. So stay tuned, stay focused. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will talk about the general strategies of verification. Here, we will talk about the common strategies that are followed in industry standard practice, so that even before the definition of the VIP, you know what things you will expect there in terms of verification related stuffs. The next point is why we need a robust verification. So this is a very important point behind having the verification IPs. Why at all we need a robust verification, I will describe with infographics. The next point is general verification flowchart. So I'll give a very generic flowchart of the verification. In actual practice, there could be addition of some blocks or subtraction of a block, or it could be arranged in a different way. So this will help you to grasp the things in a proper fashion when you go through a VIP, that is a verification IP. Next, we will come to the point, what is verification IP or VIP, which is the abbreviation. Next, we will talk about the general verification blocks in VIP, that is the block diagrams of a VIP. Next, we will talk about the verification blocks comparison in between regular test bench versus the VIP. Both are used for verification. However, there is a subtle difference between these two, and that we will point out here. Next, we will talk about the advantages of using VIP. That means, what are the advantages of having a VIP over a regular test bench? At the end, we will move out of the slide and move to the GitHub, that is through the web browser, and we will show one particular code of a verification IP which is open source, that means openly available for you to go through, understand in detail. So even there you will see the blocks will be a bit differently arranged. However, once you understand the theory from the slides, you will be easily grasping the meaning of different blocks there. And don't worry, I will provide the URL of this particular open source VIP in the video description, so that you can go to the URL, see it, and in case you are interested, you can download the codes from GitHub. So here we are done with the menu. So let us move on to the next slide. General strategies of verification. Verification IP is all about the verification, and it is like a cartridge, right? You remember the old days when the TV games were there, you had a video console there, and that time you insert one particular game cartridge into the box and that will play specific games. If you change the cartridge, right, the different games will play. So the verification IP is basically like a cartridge, but whatever is inside has a general outlook towards the verification, and that is what we are going to discuss here. First point is understand the architecture and microarchitecture. Partition logic to create efficient RTL description using moderate gate count blocks. So this is the first strategy that we'll be looking for. Next is that apply a bottom-up approach and deploy synchronizer at the top level design if needed. I have already discussed about the V-curve of VLSI. Generally, there is a specification, and from that we descend down and have a block level design. So verification happen at the block level first, and then it goes up to the SOC level and it happens there. So the verification happens in multiple stages. With this bottom-up approach, we deploy the synchronizers at the top level of the design if needed. This is one of the very key thing to remember. Use synthesizable constructs during RTL design and non-synthesizable constructs for RTL verification. Why we say that? We have an entire episode in Verilog series where we talked about synthesizable versus non-synthesizable Verilog. The Verilog has some constructs which are very useful. However, they are not synthesizable, that you cannot transfer them into gate level RTL netlist. Those constructs, however, very important, when you use them for the verification. Now, Verilog is a subset of System Verilog, and System Verilog is a HDVL, that is a hardware description and verification language, and Verilog is a HDL, that is hardware description language. So this is a very subtle difference between Verilog and System Verilog. That's why System Verilog has Verilog as its subset, and the non-synthesizable construct under whether you call it Verilog or System Verilog, they can be used for a verification purpose, because the verification decks, that means the test benches, will not be used for synthesis. And what is synthesis? We already have a series and we already have a marathon on it. Let us move on to the next point. Use blocking assignments for modeling combinational logic and non-blocking assignments for sequential logic. This is already we have discussed in detail in the Verilog series, and the Verilog series now has a marathon, so you can watch it. Avoid mixing blocking and non-blocking assignment. This is very fundamental thing, and that you understand you cannot mix the blocking and non-blocking assignments together, because already here in this point we have clarified that blocking assignments are for combinational logic and non-blockings are for sequential logic. Apply optimization constraints at RTL level to improve performance. Now, what are the constraints? Constraints are the thing that allows your verification to stay within a particular boundary. It could be a range, it could be some particular value, or anything. That means specially conditioned. So those conditions will allow not to fly off anywhere and in any direction, however, to stay within the prescribed limit. Develop a robust verification architecture and verification planning for the design. Why this robust verification method is needed, I will explain with the infographics in upcoming slides. Next point is understand the coverage requirements and implement verification strategies to meet coverage goals. And why do at all we are talking about coverage? Because generally you know a logic gate by its truth table. However, when in actual operation, there will be series of data packets that will be coming and going into a single gate. Or if the DUT is not a logic gate and it's a logic design, it will be comprising of multiple kind of gates in either in a sequential or in a combinational manner. And in that situation, you will need the coverage, that means to cover all the kind of real-time scenarios that can happen around the DUT, that is the design under test, so that your verification is exhaustively performed. However, not flying out of the field by the constraints. So here we are done with this particular slide. Let us move on to the next slide. Why we need a robust verification? Here I will show you one particular picture of a motherboard, and this will act as an infographics to you. Now let me tell you that this is from our regular desktop and that we use nowadays. So let me point out different sections. This is for connecting the hard drives, and these are the SATA ports. Here you insert the RAM. Here you plug in the processor, and on top of it there will be a fan. Here generally the PS2 ports, this is a PS2 port and this is the USB port. Generally we plug in the keyboard and mouse here, and additional USB things can be plug and play and they can be inserted here. This is RJ45 socket where we plug in our Ethernet cable, and here multiple D-shaped ports are there. It could be connected to monitor, it could be connected to a projector or anything. And here are some additional USB ports, and these are the audio ports. That means for the audio in and audio out. There are these kind of ports which will be used to insert various kind of cards. That means it could be PCI or something else. So you can understand when you are doing a digital design, say suppose for a CPU, right? It has to interact with the RAM, it has to interact with the keyboard and mouse, it has to interact with other plug and play devices like printer, scanner, it has to interact with the monitor, it has to interact with the audio devices, whether it is a microphone or a speaker, and here it will interact with the one or more hard drives that are connected. Nowadays you will see the SSD hard drives, they will be somewhere around here in a smaller shape and they will be placed in the motherboard rather than connecting using the SATA port. So in this real scenario, when you connect, and one thing I forgot to mention, sorry, here these are generally the power pins. Here the powers will be connected from the SMPS. Generally, whenever you are talking about the CPU, it will have multiple pins, right? And those pins will have a particular kind of chart for the input and output. Obviously, input pins will not give the output, and the output pin will not take as an input until or unless some pins are in bi-di. That means the bi-directional pins. So this CPU can accept multiple instructions. It can accept bus where from the data is coming and the addresses could be there. So in real time, when you turn up a desktop PC, right? So this CPU will suddenly have a rush of tides of information around it. However, when you had it on pen and paper, right? Here you have listed things. But in real time, everything will be jumping from here to here, 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 and from here to here. So all these in and out operation will be simultaneously getting performed. And obviously, the hard OS will be booted from the hard disk, so these will be in picture from the beginning of the operation of the PC. Now, you can imagine an enormous data flux is coming from all around, all on a sudden, and they are coming simultaneously. It's not that insequentially they are coming. When you have turned on, the boot sequence has been performed, the OS is loaded, and your OS interface has been ready, whether it is a Linux or it is a Windows or it is a Mac. So the user interface is ready. Now, multiple things are already started to operate. In terms of the hardware level, now your PC is ready to accept from the keyboard and mouse and show the display on the monitor and all. Those will be follow-up. Again, I talked about booting. When you are using it for, say, work, in one place, you could be playing through a music player like Winamp, and at the same time, you are working on Microsoft Office. Okay, or LibreOffice in case you are in Linux, right? So all those applications are there, and in background you are using Microsoft Edge or Google Chrome or Firefox for accessing any website or downloading any files from the internet. So simultaneously multiple operations are ongoing. So this is the real-time scenario when our EUT, that means our CPU, has to take a load from all of these kind of applications. This is a practical example that you encounter every day, and that's why I have picked this to make you understand why we need a robust verification. To incorporate all these kind of complex things can happen with the CPU. We have to write an exhaustive verification deck for the device under test. Here the device is CPU. In your case or my case, it could be a design under test. That means a block. So you understand the need of the hour of the robust verification by these particular simple infographics. And those who have not seen this motherboard, in case you have a desktop PC, you can ask your hardware engineer assembles your PC to show you whenever he comes around. Or in case you go to any hardware shop, there you can see this kind of motherboards are getting assembled inside our desktop. So this is a very sweet and simple example that will help you to understand why we need a robust verification. Because from beginning days, you know about the truth table. You will say, okay, we have a truth table kind of stuff and the device will operate like a standard defined way. However, in real time, in real life, when a chip is plugged into the board and the board has so many components and they will bombard data and address in multiple directions from multiple sequences, the design can get crashed. And the target of verification is that we will make sure that at what time and what condition this DUT, that means your block or the full SoC, can crash. So we have to crash it. That is the purpose of the verification, and hence we need a robust verification plan. So we are done with this particular infographics. Let's move on to the next slide. General verification flowchart. Folks, here I will show you a general verification flowchart. This will contain several blocks. So at the left, there will be some block, and from here we will work outside, and right side there will be block, some block. So this will happen maybe in parallel, and at some point we'll have a merger here. So wait for that. I told this to have a proper kind of idea what we are going to see. So first we have functional specification. It is also known as spec. That means we use the 4 alphabet SPEC for this. Generally, you can see as a spec, or it could be a functional specification full word. And in this direction, we will proceed. Next come the test plan. In previous slide, I have talked about that your design under test can be bombarded with multiple address and data details from multiple directions simultaneous. We have to have a good test plan. Next, we have the assertions. Now, what are the assertion? Assertion means you are saying affirmatively that this design will obey these kind of stuffs. That means it could be a port having a particular sense of operation, or it could be a bus that should be behaving in a particular way, like this. So once you go in detail of the coding, you will understand what are the assertion. But as overall, I can say assertions are way of hard coding the way the particular code or the block of code or the section of code which corresponds to our design behavior should remain in a firm way, and in case there is a violation, the verification text should flag a error or warning, whatever is applicable. Next, we proceed for hardware description coding, then RTL, and also including the UPF. So we have Verilog series, we already have UPF series, and for RTL we have synthesis series. Each of them now has a marathon, so that you can get the entire series in a single video as a marathon. In case you need to learn, you can go ahead, and we have all the resources here already in our channel. And in this arrow direction, the flow will go further forward. Now comes the linting. Linting, we already have published a linter on Tickle in this channel. You can go ahead and see that. You will find it in the Tickle playlist, or in case you search it, you will get it. The linting is nothing but a syntax checker routine that allows the engineer to verify the code even before running it, so that if there is a syntactical error or semantical error, it will be flagged by the linter tool. Linter tool could be there for Tickle, it could be for Verilog, System Verilog, it could be there for Perl, Python, any kind of language, whether it is a programming language or a scripting language or hardware description language or hardware description and verification language. Linting is a general concept, and you can find linters as resources to use them for your good. Next is simulation with assertion and checking. Here we said about the assertion. That means assertion and the code are there and it is linted. That means we have almost eliminated kind of syntactical or semantical errors. And then we simulate along with assertion and checking. So up to this stage we have reached. Now comes the bridging part. Now we have the test bench, that means with the HDVL like System Verilog, and we plug it in here. This was the hardware description and linting, and with assertions we have done some checking for the code and everything. It is ready. Now we plug in the System Verilog test bench to our design, that is the DUT. Next, we will look for the functional coverage and the code coverage. These are two detailed subjects. I will not go in detail about them, but this will make sure that the exhaustiveness of the robust verification are implemented, as I have discussed with the infographics in earlier slide. Finally, if needed, from this step, we can go back to the test bench again and we do some modification, or we may have to insert assertion or something like that as needed, and then we again come back to this stage. This loop may go around until you are satisfied that the exhaustive and robust verification is implemented. It was planned here. However, in coding, when we go for coding, we think in a way and we implement the code and then we try to check, and there is some flaw at the code level deviating from what we have thought in the planning stage. So we have to put some additional codes there to make the code go complete in nature and to tally with our test plan. And once this loop completed, then we will have the functional coverage and the code coverage, and we will have the verified RTL code and verification results. So here our verification we end and we have it verified. So here in this slide we have talked about the general verification flowchart. In actual practice, when you work in a company or you are using a particular tool, you can see there is a little modification way around this particular flowchart. Obviously, because one representation can be represented by different persons in different way and with different perspectives. So all those perspectives will be to the respective tool, person, or whoever, or maybe the verification engineer who are doing the actual verification. So this is a general concept. Keep it in mind and stay flexible that something can come in between, or this kind of flowchart may have some changes because as we are proceeding further right, many more things are getting updated and things can come in between. So this is a very simple structure to understand the verification flowchart. And why I have talked this much? Because we are talking about a verification IP. Before that, we are talking about this verification flow. As we do not have any kind of verification related video in our channel, so I have given this particular thing so that you have an idea about the verification flow. What is verification IP? Now in this slide, we will go in detail. What is a verification IP? We start with our first point. Verification IP, abbreviated as VIP, in VLSI is an essential tool for the chip design and development process. It provides standardized, reusable component to verify and validate chip functionality against specific protocols of behavior. Now, these protocols are very important. Protocols, that means how a block, specifically a standardized block, according to maybe IEEE, behaves, right? So that behavior is governed by the protocols. Verification IP is reusable, modular component and used specifically in the verification phase of a chip design. The advantageous point of verification IP is that it is reusable. It can be used again and again and again. And it's modular component. That means it is having different modules for different purposes. So this is the easiest thing. It is employed to test and validate behavior of functionality of a design under test, as we have already talked about so much in last couple of slides. Verification IP simplifies the process of providing pre-built standardized way to test whether the DUT complies with certain protocols or functions. So these are the verification tools. However, this particular kind of IPs are targeted for a particular type of design. That means for USB, you will have the USB VIP. For SerDes, you will have the SerDes VIP. So this way, one particular kind of design will have its type of verification IP. That means the design and the verification will be mapped in 1:1 manner. VIP reduces the time and effort required to ensure that a chip design works correctly before moving to manufacturing. That means this VIP will help to reduce time and your time to market will increase. Now here we are done with this particular slide. Let's move on to the next slide. General verification block. Here in this slide, we will talk about the general verification block with infographics. So let us start. Here is the infographics. You can see in the purple color, we have the SBUVM test bench, and then we have the test structure. We have the environment, then we have the agent, we have monitor, then we have created a data sequence and put it to the sequencer, and the driver will take one by one the sequence and put it to the interface element. Okay, and that will talk to the DUT, and there will be a reference model against which we will be checking. So this is a general verification infographics. Let us see some description. First, test generator, it creates the stimuli to drive the DUT. So here is the test generator. Monitor passively observes and captures DUT signal for analysis. The monitor is needed because we give an input and output, we will have a monitor, and finally we will have a scoreboard like this where all the details will be tabulated. Checker is the module that compares DUT output with the expected values for correctness. Expected values come from the reference model. Scoreboard tracks and compares transaction level data over time for consistency. That means we give a huge robust verification routine, right? And that creates multiple kind of variation and giving and injecting them into the DUT, and the output coming to the monitor, and the scoreboard will have a mapping level data mining for the verification input and the corresponding output from the DUT. And this scoreboard will be checked in detail to verify whether the design has failed or not. That means we have all the data there. In case we do not have all the data there, we'll make more kind of additions appending to the verification plan so that things become exhaustive. We're done here with this general verification block. Let us move on to the next slide. Verification blocks comparison. Now here in this slide, we will do a comparison in between a regular test bench designed by a verification engineer versus a VIP that is very much specific. So here is the table. First, we compare the test generator. For regular test bench, it is custom generated by the verification engineer, design specific and may not cover all the edges or cases of protocols. Now VIP test bench for the test generator, right? It has the protocol aware and generates a wide range of protocol compliant stimuli. Now, as I have talked, USB and PCI, all these can have their own set of protocols for data exchange. Those protocols will be much compliant in VIP with respect to a regular test bench. Monitor is a focus on signal transition and duty logic, not always protocol specific. And here the monitoring is protocol aware, passively monitors protocol compliance and transactions. So that means we also have put a tab on the protocols also here in the monitor. Checker is a custom written assertion for internal design logic, less focused on protocols. However, for VIP, built-in assertions for protocol compliance and violation. So here you can see everything is rotating around the protocol. We have the protocol too much emphasized for a VIP. Now for the scoreboard, it compares the output based on the design specification, not necessary protocol compliance. So this is the case of a regular test bench. Whereas if we take a VIP, right, the scoreboard compares protocol transactions and against expected results and track coverage. So that means here we are very much protocol aware and protocol centric approach of verification. That is the need of the VIP. Since you have already seen in the motherboard, there are several data interaction points like SATA, like the USB, like the PCI, okay, all these stuffs, right? These will have a particular set of protocol of exchanging data. Those have to be well supported by the verification and exhaustively verified for any failed cases. So here we have done a side-by-side comparison of regular test bench versus VIP test bench. Now let us move on to the next slide. Advantages of using VIP. So far we have talked about the verification need and its exhaustiveness as well as about the VIP. Now you will see what advantages will come out when you use a VIP for a protocol centric block or IP. Each VIP is configured to simulate the behavior of these protocols that the duty adheres to the specification. Here we have a standardization of the duty as well as we have the standardization of the verification decks inside VIP. For example, a PCIe verification IP will emulate the data transfer error scenarios and ensure compliance with the PCIe protocol standards. And you already saw there was a PCIe slot in the motherboard. So it's very much easy for you to visualize once we had the desktop motherboard in picture, right? You can see easily, you can touch it, you can feel it, and you can understand it. There are many such protocols for which the VIP created or available, such as now you will see the list that will make you aware in which areas the VIP have an impact. PCIe, that is the Peripheral Component Interconnect Express. So E is for Express, right? And we generally see it as a PCI Express slot in a motherboard. We have AXI, that is Advanced Extensible Interface. We have I2C, that is Inter-Integrated Circuit. We have Ethernet. You already saw a Ethernet port, that is RJ45 port in the motherboard. We have USB. Nowadays you are using USB every day and many more. Now USB not only in your PC, it's also there in your smartphone. Next point is time saving. Now we come back to the advantages, right? Here we have described the different kind of protocols that you may come across in a VIP. This is not an exhaustive list. However, you will see there are a lot of things that goes around for the VIP, and you will see multiple kind of standardization outside this list. So there are many more things there. So don't expect this is the thing that will have the only VIP and the rest of the things are not like that. So we will have a list of kind of protocols there. Time saving, reusable across multiple projects. So that means once you use the VIP, right, it is reusable code and it could be plugged in multiple projects, not only a single particular DUT design. It could be, say, there are 4 teams doing 4 type of designs, and this VIP for a particular block can be used in those particular teams by those 4 particular teams for their respective design when they integrate this particular block inside each of these design. Comprehensive testing provides a wide range of test scenarios, including edge cases. Edge means here we are talking the corner cases where we have the extremities. Standardization ensures that DUT adheres to the industry standard protocol. That means here we talk about the things should go for the specification that has been standardized, like bodies like IEEE. Automation automatically generates stimuli and checks results, reducing human error. DUTs are already a packed capsule, and once you swallow that capsule, right, it will go and burst in a particular zone, right, and it will do its work. So it will have the human error reduced. So we are done with this particular slide where we have talked several advantages of using VIP. When you enter the industry, you may come across more and more advantage by your working experience. However, this is kind of stepping stone for you to understand the VIP and its advantages. Open example of VIP from GitHub. We have talked theoretically and infographics about the VIP. Now the VIP concept is with you. Now we will unbox one particular open example from GitHub. So let us move on to the GitHub page. Hey folks, we are in our web browser and we are now visiting this particular URL. This I will provide in the video description. From there you can directly reach to this URL, and this VIP is for AXI protocol. I think the author name is Kumar Rishabh, and here you can see about it is VIP for AXI protocol, and here you can see this is a MIT license is there and you can go through it. Now if you go down further, scrolling down the page, here you can see this is the block diagram of the VIP. Now here you can see the TestBench top, and we have the test module here. Inside that we have sequence. You can find similarity with the block diagram that I have shown in the slides. However, you can see there is a difference in arrangement. Now here it is a master slave architecture, right? And we have write sequencer, we have read sequencer, we have monitor, we have driver that drives this sequentiated data into the interface, and interface will talk with the DUT. Since the DUT is not here, it is not shown because your VIP will not contain the DUT. It is the verification capsule for your DUT. So here you can see the driver is here, okay, for the slave, and monitor is here for the slave. So we have a master and slave architecture, and hence we have two different monitors and two different drivers. And finally, we have a scoreboard and coverage routine here in this block diagram. Now you have seen the block diagram, which is very much familiar, to which we have already discussed and talked about. Now I will go down further, and here you can see the list of components. So there is sequence item, sequencer 2, we have driver, we have monitor, we have scoreboard, we have environment, we have test and TestBench top, and we have environmental config and test config. Okay, all these are there. You can read by yourself and understand. Now you will have a real VIP in your hand. You can investigate in detail. How you will investigate? Let me show you. Now I do the up scroll again, and here you can see there is a lot of code. Those are uploaded in GitHub, and here you can see, let me show you the monitor code. Once I click, it will open a pane like this. It's similar to an IDE. You have in the left hand side the files, and right hand side each file open in the code viewing window. So here you can see that the monitor has several amount of code. This is in either SV or UVM. Generally you can see here it's in UVM. Okay, so you have the UVM component here, and if I scroll down, you can investigate this code by yourself. For that, at least you have to have the knowledge of systems Verilog and NPM. Next, we have the master part. We have our system Verilog code here for the master, and I think somewhere could be slave. Yeah, here it is the slave. This is the code for the slave, and here you can see it is very much protocol centric, and that's why we have its definition like this, AXI slave. And here is the code of the slave, and let me show you the driver. So here you can see the driver will contain different data width and etc. And it will have sequence items like this. So it will have tasks and functions to do the driving action. And if you go through the data, you will understand by the comments. Now let me take you to the interface, which was there at the bottom of the infographics of this particular VIP. Now interface is nothing but the port connection. So in SV, we have a method called interface where we define the different ports. Here logic means it is available only in SV, not in Verilog. So guys, you need to have the knowledge of SV to understand. And here you can see all the connections are explicitly mentioned. That means if you instantiate this particular module, the AXI INTF, right? Instantiate it. That means you can use it in a very macro way of connecting different plug and play manner, different ports. You will be doing the plug and play with this interface. So that is the beauty of the interface kind of codes in System Verilog as well as in UVM. So we have all the codes, and this is the TestBench top from where we are doing the control. And here you can see it's very simple. We have the interface instantiation and we have the clock. We scroll down, we have the configuration here. And all the things will be in very simple manner at the top level. And here you can see we have included the AXI package, the header file and the ASV file. And here is the test. So this is the detailed test thing. We have all the routines here for testing. And here is the code of the sequencer for the right one. Here is the sequencer. So you can go up to this and have a detailed view what are there in the sequencer. Again, I am emphasizing for that you have to have the basic knowledge of System Verilog at least to understand. Your Verilog knowledge will not be sufficient. So here we are done. So let me go back to the main page. So here I come back and I have shown you the code of the sequence, code of the monitor, code of the driver, write sequencer, read sequencer, core board and interface also, because there is no DUT and no reference model, right? They are not here. This is only the VIP. However, I have shown you a generic block diagram of any VIP that will operate. So you are familiar with the different set of codes. They will be there in the VIP. Now you are well aware what is the VIP, and that's all. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, please write down as comment in the comment section down below. And bye for today.